Did that work? Okay.
Yeah, we're good.
Clearly it did work. All right. And it's just about time to start. Okay. Share content, screen, start broadcast. The presentation. Okay, here we go. So welcome back to 151. We're starting the second lecture today. And I basically gave you a spiel why quantum field theory is a good thing to learn. And so let me just tell you the organization of the course this semester. So we started having a discussion on why quantum field theory is a good thing to learn. And then I'm going to actually get into these discussions on the simple systems like harmonic oscillator, creation annihilation operators, because that's what we get to use to basically formulate quantum field theory. And one interesting aspect of harmonic oscillator is something called a coherent state. And then based on that sort of review of the harmonic oscillator, then we start to actually build quantum field theory, where you actually get to see how the creation annihilation operators are used to literally create and annihilate particles. And it turns out that this the first version of the quantum field theory, namely non-relativistic Schrodinger field theory, is completely equivalent to multi-particle quantum mechanics, as I advertised on Wednesday. So at this point, you might think that you don't gain anything because it's just completely equivalent to the quantum mechanics you already know and love, but it turns out that there are many benefits, and we start to talk about those benefits. And first using the examples of the quantum field theory on a lattice, which means that not continuous space, but on discrete set of positions. For example, that's something you use actually in condensed matter physics when you apply quantum field theory to that system. And the phonon is one example where that description is actually useful. And then we talk about Bose-Einstein condensate in the cold atoms systems. And that's something people have studied. For example, Dan Stamperkern in the department is one of the pioneers in studying this. And so that's where the particles, namely atoms, start to behave like a wave. And it turns out that quantum field theory is the right description for it because the particle wave duality is really built into the system. And then we also apply the same idea to superconductors. And you might have done this already in the undergrad laboratory. So there's some piece of metal might completely lose the resistivity when you go to low temperatures. And once again, quantum field theory is the description you use to understand the behavior of the superconductor. And that also generalizes to a new concept called spontaneous symmetry breaking. And I also talk about a little bit about the spin systems like ferromagnet and antiferromagnet. Now moving in the second half of the course this semester, we would like to actually unify relativity and the quantum physics into the relativistic quantum field theory. So we first talk about electromagnetic field. That means we would like to quantize the Maxwell field of electromagnetism. And there it turns out that you also have the coherent state, which is nothing but laser or classical electromagnetic field. So using QFT, you quantize the electromagnetic field and you get a photon out. So that's what I advertised already on Wednesday, namely that this is the first time you get to see photons in quantum description. But using photons, you can also get back to the classical electromagnetic wave because that actually turns out to be the coherent state, just like in a harmonic oscillator. So again, wave-particle duality is really built into this discussion that you first start with a wave, namely classical electromagnetic wave, you quantize it, you get photons, but using photons, you can describe the classical wave once again so that the electromagnetic wave is both particle and wave, and that's what you get to see when you get to week 7. And from this point on, we'd like to actually get to use quantum field theory for practical calculations using time-dependent perturbation theory, which I believe we have seen in 137b. And by combining this quantized Maxwell field in time-dependent perturbation theory, finally, you get to actually study how the emission and absorption of photons work from, for example, the hydrogen atom. So when you start with the 2p state of the hydrogen atom, then you can emit the photon so that the hydrogen gets down to the ground state. But then you have a change of number of particles. Namely, initially, you have single electron. In the final state, you have one electron in the ground state and a photon. So that's the process where total number of particles changes. And that's the kind of system where you cannot use quantum mechanics to study, because you can't use the Schrodinger equation to discuss how the number of particles can change, where number of arguments in the wave function should change if you stick to the quantum mechanics. So that's something I advertised already Wednesday. You absolutely need quantum field theory to study that kind of the process and phenomena. And that's the first time you actually see this in week 9. And at this stage, the electron is still treated non-relativistically because you're talking about the Schrodinger equation for the hydrogen atom. But ultimately, we need to actually make everything relativistic. So to really make sure that everything is relativistic and quantum, you have to define a relativistic field theory for every particles and waves. So we first do a little exercise with spin zero particle, and that is to Klein-Gordon theory. And one of you were already asking questions about this. But ultimately, we need to understand spin 1/2 particles like electrons, protons, and neutrons. And that's when we talk about Dirac theory. And it turns out that when you apply quantum field theory to Dirac theory, it turns out that that leads to the prediction that the antimatter exists, and hence the positron for electron and antiproton for proton, and so on and so forth. And
Sorry,
once you
we
have
have a
everything,
question in the chat.
oh, go ahead. Thank you.
So the question is, are the fields upon which quantization do not give particles?
Can you say that again?
Yeah, it reads, are the fields upon which quantization do not give particles?
They do, yeah. I'm not sure I answer the question. So whenever you start with a field, and when you quantize the field, you always get particles out. But that particle, of course, is also at the same time a wave because of the particle wave duality. So when I, for example, mentioned the week 7, you start with the electromagnetic field, just like what you study, I think, in physics 7. And when you quantize it, then you get the photon out. But it's not particle without being a wave. It's particle at the same time being a wave. And so that's where you apply the idea of the coherent state, which I'm gonna, I hope I get to discuss it today, where harmonic oscillator is a quantum system, once you quantize it in quantum mechanics, but at the same time, it should be able to describe the classical pendulum. So using harmonic oscillator as an example, you get to see, you start with a classical particle, you quantize it, and you get the wave function out. But at the end of the day, this quantum harmonic oscillator should be able to describe classical pendulum too, because the quantum mechanics is a not jump from classical mechanics, but it's supposed to contain classical mechanics in it. That's why quantum mechanics supersedes classical mechanics. Classical mechanics is part of quantum mechanics. So the quantum harmonic oscillator should be able to describe classical pendulum. And that's where we talk about the coherent state. And in the same way, when you start with the classical field, when you quantize it, you get particles out. But that description should be able to also describe classical wave at the same time, because the quantum field theory should describe the wave-particle duality as a whole. So after quantizing the field, not only you get a particle out, but also a description where a particle can also behave like a wave at the same time. So you get basically both out within the formulation of quantum field theory. Am I answering a question? Who asked this question?
Yeah, he says that answers it. Thank you.
Okay, good. Okay. All right. And then once you actually unify relativity and quantum field theory, then it turns out that you get lots of predictions. So antimatter is the first prediction that comes out of it. But at the same time, that you get also some more quantitative the theorem that the particle and antimatter antiparticle have the same mass, same lifetime, and various other things you actually also show about the behavior of particle and antiparticle, and that is what is called the CPT theorem. And also, I tell you that there's a theorem now, spin statistic theorem, that tells you that the spin integer particles should always be boson, and spin half-odd particles should be fermion. And that's something you already know, that the electron, proton, and neutrons are all fermions, and a photon is a boson. So that sort of is more generalized, and it is actually not something you impose on quantum mechanics, but it turns out to be an outcome of the relativistic quantum field theory. And trying to bring everything together, then you find a tool how you actually compute the perturbation theory in quantum field theory, in particular quantum electrodynamics. That's really the unification of quantum mechanics, Maxwell's theory, special relativity, and some nuclear physics like gamma decays into a single framework, very predictive. You have very concrete way of doing calculations with it, and that's based on this idea called Feynman diagrams. And finally, if I have time left, I'd like to cover whatever that might be interesting at that point as a topical material. So that's the organization of the course this semester. Okay, so that's the idea. Any questions about this? No? All right, so let me then jump right into the content. So the first thing I need to do is a brief review of the Lagrangian and Hamiltonian in classical mechanics, because that's what we actually always take as a starting point. So always I talk about Lagrangian as the beginning of the discussion on any systems. So the reason that you actually have seen Hamiltonian most of the time in quantum mechanics class is because you have been dealing with non-relativistic systems. But it turns out that Lagrangian is much better starting point, because that would actually make all the symmetries of system manifest, including the Lorentz invariance as we need in relativistic systems. So we most of the time start with the Lagrangian to discuss any systems. And once you have a Lagrangian, as I believe you know, that gives you the equation motion called the Euler-Lagrange equation. So that's the idea, that once you have a Lagrangian, that tells you how the equation of motion is derived from it. So the Lagrangian is the beginning of the discussion that gives you the equation of motion in, for example, Newton's mechanics in the case of non-relativistic system. But at the same time, Lagrangian determines what is called the canonical structure, namely that Lagrangian tells you what X and P are in a given system. And also Lagrangian gives you all the symmetries in the system. I mentioned already that the Lorentz invariance is incorporated, and the Lorentz invariance, as I already mentioned on Wednesday, have to treat time and space on equal footing. And if you use Hamiltonian, time is dealt with completely separate from space, because the possession is an operator, time is a parameter. If you go to Lagrangian, the time and position are treated in much more uniform way. So that's the only way we can talk about Lorentz invariance, and that comes later in the second half of the class I mentioned just a minute ago. So that's the main reason why we like to get started with Lagrangian. So once again, Hamiltonian treats time differently from space, but we like to treat the Hamiltonian time and space on equal footing. That's why we would like to actually use the Hamiltonian instead of Lagrangian. Now, with the iPad, I don't control the slides very well, so I apologize. So let's see. Yeah, and the word Lagrangian, you might actually wonder why Lagrangian has the IAN at the end, not EAN, according to Lagrange. And that's because the Lagrange was actually an Italian from in its birth, and Giuseppe Luigi Lagrange became Joseph Louis Lagrange, so that he actually moved to France and got naturalized. So Lagrange is the name we always refer to. But when you talk about Lagrangian, we actually respect his Italian origin and use GIA instead of GE towards the end of his name, and hence Lagrangian and with an I in it. So, it's interesting that people used to move around in Europe already at that time. And that's what physicists do. I originally from Japan, I live in the United States, and people really do move around still because the physics, mathematics are really true and the universal for the entire planet. So that is already one of the examples where people actually did that already. Okay, so hopefully this works now. So Lagrangian, that's why we talk about that. And so Lagrangian is L as a function of T, where the T dependence comes through the X in the Lagrangian. And hopefully you have seen this in some of the classes you have taken before, but if you have not, I already have the lecture notes posted on B courses. That's a review of the classical mechanics using Lagrangian and Hamiltonian. So please look at that lecture notes. And of course, you're welcome to ask any questions about this. So using the Lagrangian L, you integrate Lagrangian over time, and that defines what we call the action S. And as I already mentioned, Lagrangian is a function of position Q, and its time derivative Q dot. And so whenever you have a dynamical system, you try to describe the dynamical system using some kind of variable, and Q is the variable in this case. And then you have Q as a function of time, and you also specify time derivative of Q dot, and the Lagrangian is supposed to be a function of Q and Q dot. So that's the Lagrangian. And when you go to field theory, Q is actually a field. So that also depends on space. But we start with the particle, the mechanics first. So at this moment, you can think of Q as just the position of a particle. And of course, when you describe Newtonian mechanics, the position of a particle changes as a function of time. That's the motion of the particle. So X is a function of T, that's Qi. And you also specify the velocity of the particle, X dot, that's Q dot. And as we all know, the mechanics is completely fixed and it's predictive once you specify the initial position and initial velocity of the particle. And hence you specify Q and Q dot at a given time. And that is supposed to give you all the predictive power on what is going to happen at the later times. So Lagrangian is a function of the position and the velocity because of that reason. So you always find the Lagrangian to be a function of whatever the variable you use and its time derivative. So that's the Lagrangian. And using the Lagrangian, the first thing you do is to derive what the canonical momentum is. So in the case of particle mechanics, Lagrangian contains the kinetic energy, half mv squared. And v is, of course, x dot. In taking the derivative of Lagrangian with respect to x dot, you define the momentum that's mv or mx dot. And I will show that explicitly in a moment. So that's the very first thing you do whenever you find the Lagrangian. And using P, I just defined, next thing you do is define the Hamiltonian. So Lagrangian is a starting point that allows you to define what the momentum is. That's how you set up the canonical commutation relation once you go to quantum mechanics. And also that allows you to define what the Hamiltonian is. So Lagrangian is the beginning of everything. So if you start with the Hamiltonian, you need to know ahead of the time what is P, which is canonically conjugate to Q. But if you start with the Lagrangian, that is also derived. So once you start with the Lagrangian in action, then you can derive everything about the system, while when you start with Hamiltonian, you have to have additional input. So that's why Lagrangian is a good starting point, even though in quantum mechanics class, you probably have started with Hamiltonian from the very beginning, and then you are told that P in the system is what is canonically conjugate to X. But that's something that is derived if you start with the Lagrangian. So that's why Lagrangian is a better starting point to discuss any dynamical systems. Okay, so now that you have derived what P is, and what you have derived what Hamiltonian is, next thing you do is set up the canonical quantization, the commutation relation between Q and P. And that's something you have seen already in quantum mechanics class. Then you are now dealing with a quantum system. And then you actually start defining the wave function and its time evolution, and hence the Schrodinger equation. So the simple example of the Lagrangian for particle mechanics, so here I'm talking about just a simple harmonic oscillator. So you have X as a position of a particle, and you have a harmonic oscillator, so you have the potential energy, which is quadratic in X, and that's the second term in the Lagrangian. And as you might recall, Lagrangian is given by kinetic energy minus potential energy. So kinetic energy is half mx dot squared. Potential energy is half m omega squared x squared. So kinetic energy minus potential energy is what you see here as the Lagrangian of a harmonic oscillator. And once again, you can see explicitly that Lagrangian is a function of both position, in this case x, and its time derivative x dot. So what you see is the correspondence to what I have on the left-hand side of the slide. Now you have Lagrangian as a function of q and q dot. So I just follow what I have on the left-hand side of the slide. The next thing I'm supposed to do is define the canonical momentum. I take the derivative of the Lagrangian with respect to the time derivative of the degree of freedom x. So del L del x dot is P. And then you can easily see that P turns out to be mx dot. So that's something you, again, derive from the Lagrangian. That's not additional input. Once you have the Lagrangian, you know exactly what the momentum is now derived from the Lagrangian. And then you define what the Hamiltonian should be. So the Hamiltonian is Px dot minus L. So on the left-hand side of the slide, I write PQ dot minus L, but in the case of harmonic oscillator, Q is nothing but the coordinate, namely position of the particle. So that's Px dot minus L. And the interesting thing about Hamiltonian is that it is supposed to be a function of x and p. You are not allowed to use x dot in Hamiltonian. So that's why we actually can write down the Schrodinger equation using Hamiltonian, where x is the eigenvalue of the position operator, and p then is written as h bar over I times x derivative. I hope you have seen that in 137. So Hamiltonian is supposed to be a function of x and p, should not depend on x dot. So what it is supposed to do then is that you first write px dot minus L, because that's the definition, but then you try to rewrite x dot using p. So you eliminate x dot completely from the expression for the Hamiltonian. So px dot is then written as p times p over m, because what I derived on the second line here on the right-hand side of the slide is p is mx dot, because that's the x dot derivative of L. So using this, I can rewrite x dot as p over m. So that's why px dot is now p times p over m. And I do the same thing for this minus L. So inside L, I have x dot. So you rewrite x dot using p over m. So that's what I have done in the square bracket. So now Lagrangian is half m and p over m squared, that's the x dot squared, minus half m omega squared x squared. So by expanding this square bracket, and the first term cancels p x dot, at least is half of it. So you end up with p squared over 2m. And then the potential energy now changes its sign because of this over minus sign in front of the Lagrangian. And so then you have this potential energy now added to the kinetic energy. So you find this familiar expression of the Hamiltonian for the harmonic oscillator, p squared over 2m plus half m omega squared x squared. So that's what you probably use as a starting point of the discussion of the harmonic oscillator in the quantum mechanics class. But now you see the Hamiltonian is actually derived from the original Lagrangian that's actually on top of the slide on the right-hand side. So that's how you always begin with the Lagrangian. Then from the Lagrangian, you define what the canonical momentum is. And using canonical momentum, you define what the Hamiltonian is. And that's what we have done already right here. And using this Hamiltonian, the last thing you need to do is set up this canonical quantization condition, namely X and P are now operators. They don't commute because they are not numbers, they are now operators. And XP commutator, namely XP minus PX, is IH bar 1, if I and J refers to the same degree of freedom. And so this is maybe a little generalization of the harmonic oscillator you have seen in quantum mechanics class, because I have subscript I to X. So in principle, I will be talking about many X's, which correspond to many particles. And each particle is described by Xi and its time derivative Xi dot. And for each Xi dot, I now introduce Pi as a canonical momentum. And then I have many Xi's and many Pi's. And so the canonical commutation relation is X and P gives you IH bar when they refer to the same degree of freedom I. But if you're talking about different particles, their X and P would commute with each other. So hence you have this delta Ij. So delta Ij, you probably know, is a simple Kronecker delta that it's 1 when I and J are the same, but it's 0 when I and J are different. So that's how you start with the Lagrangian and define the system. And this is what is called the quantization. And the reason why we call this quantization is when you talk about Lagrangian, you're still thinking about classical system. But at the end of the day, when you set up this commutation relation, now you're talking about operators, and then you're talking about quantum systems. So this is the standard process of quantization. You start with the classical mechanics defined by the Lagrangian, then you define what the quantum system is, hence quantization. So we keep doing the same steps over and over again in the course of this semester. So this is something you need to have in your mind very clearly. Every time you see a Lagrangian, we go through the same steps. So this is a good point to stop if you have any questions.
I have a quick question.
Go ahead.
So is the commutation relation that we have written between the momentum and its integral, is that an assumption of the theory, or is that a derivation? I mean, in quantum mechanics, we actually derive the commutation relation. Is that an assumption in quantum field theory?
Yeah, so it is an assumption in the sense that classical mechanics doesn't know quantum mechanics. You have to make a jump from classical mechanics to quantum mechanics. Quantum mechanics contains classical mechanics, and namely that if you send the h bar to 0, you are supposed to recover classical mechanics. And indeed, you see that because XP commutation relation is proportional to h bar. So when you send h bar to 0, this goes to 0. Hence, X and P commute. That's why you don't need to think about operators anymore. X and P just become numbers. But going from classical mechanics to quantum mechanics, because classical mechanics doesn't know about quantum mechanics, classical mechanics doesn't know about h bar, you have to make a jump. And so the general rule is that in classical mechanics, people already talked about something called the Poisson bracket. And I really don't know why people invented Lagrangian and Hamiltonian to deal with the classical systems. And so in retrospect, the Newtonian equation of motion is everything you need in classical mechanics, right? If you have a harmonic oscillator, we don't need to talk about Lagrangian or Hamiltonian. All we need to know is the equation of motion, namely ma, that's the force, is given by minus m omega squared x. That's the Hooke's law. And once you know the Hooke's law, namely F is negative mx omega squared x. Hooke's law tells you the force is proportional to the distance. And then you know what the Newtonian equation of motion is, F equal ma. And then you can solve it and find the motion of the pendulum. That's all you needed to know. But for some reason, the physicists and mathematicians in 19th century decided to reformulate the classical mechanics by inventing this idea of the Lagrangian. And that's the reason why we can talk about the principle of the least action. So the least action is the way you can derive Newtonian equation of motion. And using Lagrangian, now you can define Hamiltonian, that is meant to be energy of the system. And then the 19th century physicists invented this Poisson bracket that you have something similar to the commutation relation between X and P. But for some reason, that reformulation of the Newtonian mechanics using Lagrangian and Hamiltonian turned out to be exactly what you would need to do this quantization, to make a jump from classical mechanics to quantum mechanics. And then the classical mechanics, once you define the Lagrangian and Hamiltonian, you know this procedure, how to make this jump. So everything down to the point of writing Hamiltonian is still classical mechanics, but all of a sudden you introduce this commutation relation, and now you're talking about quantum mechanics. So this is a step of the quantization. So once again, in classical mechanics, you didn't need Lagrangian and Hamiltonian. All you needed was Newtonian equation of motion, F equal ma. But for some reason, people invented Lagrangian, Hamiltonian, and language of canonical momentum and coordinates. And that language turns out to be the language you need to define a quantum system. The only thing you need to do from classical mechanics to quantum mechanics is to assume that this canonical quantization is among the operators X and P. So here, it's a jump. You are going from classical mechanics to quantum mechanics by accepting that X and P follows this canonical commutation relation as operators. And you're going from now numbers X and P to operators X and P because they satisfy this algebra of the commutation relation. And that's the jump you have to make. And you have to make a jump because classical mechanics doesn't know quantum mechanics. I'm repeating myself here. So this jump is absolutely necessary because, again, we mere mortals haven't experienced quantum mechanics in a daily experience. So that's why we have to make a jump in some form of mathematics to go from classical mechanics and quantum mechanics. And thanks to God, somehow we have formulated classical mechanics in such a way that we can use the same language to talk about quantum mechanics using Lagrangian, Hamiltonian, X and P. And so I find this really miraculous that the human beings were able to invent this language before knowing anything about the quantum mechanics, but we already had the correct language to talk about quantum mechanics even before the quantum physics was invented. Okay, so did I answer your question?
Yeah, that answers it. Thank you.
Okay, good. Any other questions at this point? I barely hear you. You sound very soft.
I have a question. Can you hear me now? It's still
Oh, go ahead.
The question is, first, so we have action S, and action is related to Lagrangian. Besides the very useful least action principle, is there a reason why we don't use action that often?
We actually do use action often when you talk about quantum field theory. So the only reason why you don't use it very often is because in the quantum mechanics class, you probably started with the Hamiltonian from the very beginning. And with the Hamiltonian, you don't define action because then you have to go back from Hamiltonian to Lagrangian and define the action. So you actually don't do this most of the time. But as I emphasized already on Wednesday, we eventually would like to go to relativistic systems. You have to implement Lorentz invariance and want to treat space and time on equal footing. then it turns out that the action is the only way to do so. So at this point, I'm talking about the particle mechanics. So the Lagrangian is a function of x for the harmonic oscillator, but eventually Q becomes the field, and hence we are talking about the field theory. And Q then is a function of both x and t. And then you integrate Lagrangian as a function of t, but also as a function of x at the same time. So action turns out to be a space-time integral when you go to field theory. So that's how we end up treating position or space and time on equal footing. So the action turns out to be the correct starting point. If you define Hamiltonian, then you don't need to go back to the action to talk about the system, because you end up writing the Schrodinger equation. So you can, in principle, forget about the action, but it turns out the action is the only way you can make sure that your system is Lorentz invariant and hence relativistic. So it turns out that we will be using action all the time once we get to the field theory. That's something you have not done in quantum mechanics class, only because you only dealt with non-relativistic systems. But when you actually try to combine relativity and quantum mechanics into the relativistic quantum field theory, then you have to really start with the action, because that's the only way you can treat space and time on equal footing.
I see.
Does that answer your question?
Yes, I have another question.
Go ahead.
Another question will be, only if we learned in classical mechanics course, we know that only when time is independent, the energy will be equal to the Hamiltonian. So if we study the time-independent Schrodinger equation, Hamiltonian operator automatically fulfills the requirement of giving us the energy of the system. However, if we now are talking about the time-dependent, for example, Lagrangian or time-dependent systems, then how to modify, or in a more general sense, how do we make sure that the Hamiltonian is giving the energy as we want it?
Well, that actually depends on the system. So if you have, for example, the external field, if you talk about, for example, with a particle with a spin, you can apply external magnetic field to it, and you can also make the magnetic field time dependent. Then there's no guarantee that Hamiltonian ends up being the energy. And in particular, energy is no longer conserved anyway. And that's the Noodle's theorem. So Noodle's theorem tells you only when you have certain symmetry, in our case, time dependence is a symmetry, because you can define time with whatever origin you take. That's called a time translation invariance. And that gives you the conservation law that energy is a constant in time. But once you have the time-dependent magnetic field acting on a spin of the particle, then energy is no longer conserved. So it's actually not a very useful quantity to talk about. Hamiltonian is still a convenient quantity to talk about, because that defines the time evolution of the wave function. And the Schrodinger equation is always written with a Hamiltonian. So Hamiltonian is still important, but energy is no longer conserved in that case. So it turns out that once you have the time-dependent, the Lagrangian Hamiltonian, then the Hamiltonian is still useful as a time evolution. Hamiltonian is what pushes time forward. We'll get to talk about this also probably next week. But the energy is no longer conserved quantity, so that's actually not a very useful quantity to talk about anymore. So Hamiltonian, in some sense, is more important than energy, and energy may or may not be conserved depending on what system you are talking about. The Hamiltonian is always important, because that's what defines the time evolution of the system according to the Schrodinger equation. Am I answering your question?
Yes, I have one last follow-up question.
Okay, go ahead.
So you mentioned that Lagrangian is a better starting point than Hamiltonian because it preserves the symmetry or conservations. From my understanding, conservations can be tested using Poisson bracket with Hamiltonian. So why are we using, I don't understand at which point does Hamiltonian not being able to display the symmetry or the useful like Lorentz invariance?
Yeah, so when you write down Hamiltonian, then Hamiltonian defines a time evolution. So you are singling out time. And so when you actually have a Hamiltonian, then you can write down the time evolution of P and Q using the Poisson bracket, as you mentioned. And if anybody in the class is not familiar with Poisson bracket, don't need to worry about this. You can find that in my lecture notes. And also, the only way you can you refer to Poisson bracket is when you actually talk about this commutation relation in quantum mechanics. So you don't need to really know about Poisson bracket in classical mechanics. So don't worry about that. But I think that's Ian, you're asking question. So that you can define this time evolution of every operator using Hamiltonian. You can derive this Poisson bracket. So you're completely right. Once you have a Hamiltonian, and if you know the Poisson bracket, then you can derive everything you need about the system. But in addition to Hamiltonian, you do need to know what the Poisson bracket is, namely that you do need to know what P corresponds to what Q, and that's something you have to put in by hand using Hamiltonian language. But if you go back to Lagrangian, you can derive what P is for each Q. So Poisson bracket or canonical commutation relation quantum mechanics is something you know derived from the Lagrangian. That's not an external input. So Lagrangian gives you two things. It tells you what P is for each Q and what Hamiltonian is. And you need to know both to set up the quantum system, namely the canonical quantization, canonical commutation relation. And Lagrangian knows them both, but Hamiltonian is only half of the information. So that's why the Lagrangian knows better about the system. And in particular, it knows better about the symmetry of the system. Does that answer your question?
Yes, thank you.
Okay. Okay, then let me move on. So this is just a brief review of how you go about from the Lagrangian and define P, define Hamiltonian, and set up the commutation relation, and hence you have quantized the system. And we keep doing that. And once you know what the Hamiltonian is, then that immediately tells you the Schrodinger equation. So you have seen this over and over again in 137, when you have a state given by this ket, and then time derivative of the ket times IH bar is given by this Hamiltonian operator acting on this state and given by this ket vector. And knowing that Hamiltonian is function of Q and P, and we have derived this canonical commutation relation from the Lagrangian. So you know this the commutation relation between Q and P that allows you to define, for example, the position eigenstate. This is Q bra. This is an eigen bra of the operator Q. And knowing this canonical commutation relation, you know that P can be written as a derivative with respect to Q times H bar over I to satisfy this commutation relation. And using this Q bra, you can define this inner product of Q bra and state ket psi, and that defines the wave function. The psi is now a function of Q and T. And using this idea that the momentum operator is given as the derivative operator with respect to Q, you can write down the differential equation for the wave function psi of Q and T. So in the initial formulation on the first line, psi is a sort of abstract vector in a Hilbert space, which doesn't depend on Q or P. It's just an abstract ket that depends only on time. But using this idea of taking inner product between eigenbra of Q operator and the state ket psi, you can define this wave function that depends both on Q and T. And then Hamiltonian is now acting as a differential operator on this wave function psi of Q and T, where you replace every P in Hamiltonian by this derivative operator H bar over I del del Q. So that's how you define the Schrodinger equation for the wave function. And you might have started with the bottom half of the slide, starting with the Schrodinger equation for the wave function, and have gotten to this abstract idea of ket vector and bra later on. But anyway, so this is just the same formulation, starting with this abstract ket vector psi to the explicit the Schrodinger equation, wave function. And once again, we apply the same idea for the Hamiltonian. We have defined this Hamiltonian on the previous slide, starting with the Lagrangian. So now we have the Hamiltonian, but we have already also derived this XMP canonical commutation relation. So that's why we know that P operator can be written as h bar over I del x. So using Hamiltonian, I replace P by h bar over I del x. So that's how the first term, P squared over 2m, now becomes the derivative operator, which has a second derivative in x. And the potential energy term in the Hamiltonian is given in terms of x. So I don't need to do the replacement. So in the Hamiltonian expression, x is an operator. But because we have taken this position space, the representation, x is now the eigenvalue of the x operator. So if you want to really distinguish between x operator and x eigenvalue, I may have put x with some hat or some boldface in the Hamiltonian, and x as just the ordinary x in the Schrodinger equation. But anyway, so I hope that's clear. So in the Schrodinger equation, in the coordinate space, x is now the eigenvalue of the position operator, and hence x is now a number. But that comes with a cost that momentum is now a derivative operator with respect to x, because something has not to commute. So once you define x as an eigenvalue of the position operator, it looks as if x is now a number, but you still need to satisfy the commutation relation between x and p, and that's why p has to be now a derivative operator that doesn't commute with x. So that's how you define the Schrodinger equation in quantum mechanics. And what you see in this expression, though, is that Hamiltonian is something that moves time forward. Namely that when you act Hamiltonian on a given state, that defines time derivative, and time derivative is pushing time forward by an infinitesimal amount, right? So derivative is always changing the variable by infinitesimal amount. So here we are changing time by infinitesimal amount. So acting Hamiltonian is the same thing as the pushing the time forward. So that's why I said that Hamiltonian is a time evolution operator. So Hamiltonian dictates how the dynamical system changes as a function of time. And that's what we need to understand. Whenever you see a physical system, you would like to understand its dynamics. And dynamics is just a word used to describe how something changes in the course of time. That's the motion or dynamics of the system. And Hamiltonian gives you this dynamics because Hamiltonian pushes the time forward. So Hamiltonian is a very important operator because of the reason. So anyway, so this is what you always have done in quantum mechanics. So now we start with the Lagrangian, and that defines Hamiltonian and canonical commutation relation. And once you know both, namely Hamiltonian and commutation relation, then you can always define the position space representation where the operator Q is in an eigenstate. And using that position bra, you can define this wave function. And now you can derive what the Schrodinger equation is to describe time evolution of the system. So the idea is that once you have the Lagrangian, then everything else follows. And again, this is something we do over and over again in the course of this semester. We start with the Lagrangian that defines Hamiltonian, that defines canonical commutation relation. And having both Hamiltonian and commutation relation, then you can derive what the Schrodinger equation is to describe the dynamics of the system. And then you try to solve it at the end of the day, of course, and try to understand how and make predictions on how system evolves as a function of time. So that's the idea of going from classical and quantum mechanics. Okay, go ahead with the question.
I have a question about the left-hand side of the slide, the fourth equation. can I ask what exactly does it mean? Because the left-hand side, I see a wave equation, and the right-hand side, I saw a bracket, which is essentially meaning scalar. However, I don't understand, like the bra state of Q means, is it an eigenstate or is it just a variable? Because I don't know how to treat Q from the left-hand side to the right-hand side. The left-hand side looks like an equivalent, like a parameter, but the right-hand side looks like it's a state of Q. So I don't quite translate here.
Yeah. So here I'm a little bit sloppy because I'm using the same symbol Q to represent both the operator for the position and its eigenvalue. So that's why I'm probably confusing you. So Q is an operator, and that's why I can define the eigenstate of the Q operator, and that's this bra Q. So this Q in the bra notation is the eigenvalue of the position operator. So when you act Q operator on this Q bra, that gives you eigenvalue Q.
Okay.
So that's why I'm using the same Q for both operator and eigenvalue. I apologize. So that's probably a confusing thing I have done. But anyway, so in Q bra, this Q is meant to be a number that is the eigenvalue of the Q operator.
Okay.
So when I take this inner product of Q bra and state get psi, Q is already a number because there's an eigenvalue of the Q operator. And so the left-hand side, psi of Q and T, the Q in psi is already a number. So that's what we mean by the position representation, because taking inner product between Q bra and state psi, that defines the probability amplitude of the particle psi being at the position Q. And that's the wave function. If you take the absolute square of psi, then that defines the probability of a particle being at the position Q, as you have seen, I'm sure in quantum mechanics class. So this is the probability amplitude, and that's defined in this abstract fashion in a Hilbert space as an inner product of the state psi, represented by this ket, and position eigen bra, that's the Q bra, and that inner product gives you this probability amplitude, which is nothing but the wave function. Does that answer your question?
Yes. Then can I ask about the equation above, like just above it? So does it mean like this, the left-hand side, the Q bra means that it is the operator, where no, it's not an operator. Is it the eigenstate? Should it be the eigenstate?
That's right. So Q inside bra is already the eigenvalue, namely a number.
Yeah.
And that's why I can define Q derivative.
Okay.
If Q is still an operator, there's nothing I can define as a derivative with respect to an operator. But once that Q is a number, I can define that.
Okay, thank you. Thank you.
Anybody else?
Hi,
Wants...
Arthur, can I ask?
Oh, go ahead.
So in classical mechanics, we can like choose the generalized coordinates, the set of generalized coordinates to describe our system. So like, how can we guarantee that the canonical quantization condition gives the same Hilbert space and the same time evolution when we change from one coordinate system to another coordinate system?
Yeah, that's an excellent question. So it turns out that changing Q to a more general variable Q is always given by some kind of a unitary transformation. So when Q and P satisfies this canonical commutation relation for a given set of the coordinates, then new set of coordinates, Q and P, so let's say Q prime and P prime, is unitary equivalent to the original Q and P. And so that's the idea that how general coordinate transformation in classical mechanics becomes a unitary transformation in quantum mechanics. And because it's unitary transformation, when you change Q to U, Q, U inverse, and P to U, P, U inverse, then you can factorize U out of this canonical commutation relation, and then right-hand side becomes U, IH bar delta IJ, U inverse. But IH bar delta IJ is a number, so that commutes with U operator. So then you can class U and U dagger, that becomes 1. So you find IH bar delta IJ once again. So the idea is that when you go to general coordinates, we're always defining a Q going to another Q by unitary transformation using the operator language in quantum mechanics. But IH bar delta IJ is a number, so it is the same no matter what unitary transformation you perform on the operators Q and P. So that's how it is always guaranteed that the canonical commutation relation stays the same no matter what choice you make on describing a system with whatever choice of Q you make. Does that answer your question?
Yes, thank you.
Okay, good. And we also talk about the unitary transformation later on, so you get to see that more explicitly later. So I hope that actually gives you a better idea on what I'm talking about now. Any other questions? Okay, so I told you how you can start with the Lagrangian to define commutation relation, defining Hamiltonian. Once you have done both, then everything else follows, namely that at the end of the day, you get the Schrodinger equation, and then you just go ahead and solve it to understand the dynamics of the system. And going back to this, the abstract expression, the time derivative of psi ket is given by the Hamiltonian operator acting on psi ket. You can find this formal solution to this equation, namely that psi at the time t is given by the psi of time 0, that's the initial condition, with this, again, unitary operator, e to the minus iht over h bar. So once you actually take this form and take the time derivative, that's the first equation on this slide, then you can see the Hamiltonian is pulled out from the exponent. So h is now acting on the state as the whole. But this right-hand side is nothing but the left-hand side, namely psi of t, so that you can demonstrate that it does satisfy the equation, the first line on the slide. So the formal solution to this time evolution equation is that e to the minus iht over h bar is the unitary operator that tells you how the system evolves as a function of time, and hence Hamiltonian is the time evolution operator. So we use this idea again over and over again, especially when we get to talk about the perturbation theory and start talking about actual computations. So the Hamiltonian is something very special, and then this is actually what moves time forward. And so we use this idea over and over again. Yep, so I'm just saying this now written on a slide. And that gives you also the notion of the stationary states. Something being stationary in classical mechanics is nothing is moving. In quantum mechanics, stationary means that the state changes only by an overall phase. So now that we know the Hamiltonian is what pushes time forward, and it's an operator, so you can talk about its eigenstate. So H acting on the state psi gives you the eigenvalue E. And once this state is an eigenstate of a Hamiltonian operator with the eigenvalue E, then your original time evolution equation becomes very simple, because time derivative simply gives you the eigenvalue E. Then you can immediately solve this, that the time evolution of the state psi is given only by the overall phase. And as you know already, in quantum mechanics, you always take the absolute squared to define the probability. And when you take absolute squared, overall phase factor drops out. And overall phase factor is only dependent on time for this state, which is an eigenstate of the Hamiltonian. And therefore, the time dependence completely drops out from everything. So that's the quantum analog of the idea that nothing is moving. And that's what we mean by stationary states. In the case of the Hamiltonian for the harmonic oscillator, we have this Hamiltonian p squared of 2m plus half m omega squared x squared. And we now talk about the eigenstate of this Hamiltonian operator with the eigenvalue E. And then you just go ahead and write this the eigen equation using the wave function psi. in the coordinate space. So once again, the P is now replaced by h over I times x derivative. So P square over 2m is now a derivative operator acting on a wave function of psi. Now x is an eigenvalue instead of the operator in the initial part of this slide. And then this eigen equation of the Hamiltonian is now written as a differential equation, ordinary differential equation for a wave function that depends on x. And then you go ahead and solve this. You have seen this in quantum mechanics class. That's given in these Hermite polynomials, Hn. And I don't get into more details here, but that's the solution to this equation. And you also find the eigenvalues of the Hamiltonian from the requirement that the wave function has to be normalizable. Namely that once you take absolute square of x and integrate over x, that should converge. It should give you the finite norm of the state. And that fixes this overall normalization factor in front of Hermite polynomials. And so that requirement then also fixes the energy eigenvalues to be quantized in a unit of h bar omega. So that's something you know already from quantum mechanics class. So once you start with the Lagrangian, we define H and commutation relation, that defines the Schrodinger equation, then that allows you to then solve the system by looking at these stationary states, namely eigenstates of the Hamiltonian. Okay, so I'm sure you have seen this before, but are there any questions about this? Okay. Probably just looked familiar enough. And once you have this eigenstate of the Hamiltonian, and in this case, we're talking about time-independent Hamiltonian, then eigenvalue of the Hamiltonian really does have the meaning of the energy of the system. Okay, so now we have defined, so we have talked about this general idea, how to go about from classical Lagrangian to the quantum system, and eventually the Schrodinger equation. So we now specifically talk about a harmonic oscillator. And the reason why we talk about harmonic oscillator is partly because it's just a review of something you have seen before, but also because we end up using harmonic oscillator to define the quantum field theory, namely that we will be talking about creation and annihilation operators. So it turns out that quantum field theory is basically an infinite collection of harmonic oscillators. So for this purpose, it's very useful to recall this algebraic method introduced originally by Dirac, if I understand correctly, to talk about creation and annihilation operator for the harmonic oscillator. So in classical mechanics, harmonic oscillator has this Hamiltonian, basically given by p squared and x squared. So it's very natural to think of p and x as added in this quadrature as a sort of absolute squared of a complex variable x plus ip. So if you have, let's say, x squared plus y squared, you can rewrite x plus y squared as the absolute squared of the complex number x plus iy. So x and y are real. X plus iy is a complex number, and absolute square of the complex number is x squared plus y squared, real part squared plus imaginary part squared. So what we are doing here is exactly the same idea. So once you have p squared plus x squared, then you can write it as the absolute square of x plus ip. And of course, you have to fix that up with these factors of m and omega n. So far, this is just the rewriting of the Hamiltonian. But at this point, you have to remember that we are no longer talking about classical mechanics. So x and p are not numbers anymore, but they are operators. And they satisfy this canonical commutation relation, xp minus px is ih bar. So we have to be a little more careful when you actually take this approach of rewriting Hamiltonian using the complex number. And because x and p don't commute anymore, it turns out when you do this rewriting, you have to make sure that p and x are no longer numbers, but they are operators. And to reproduce the original expression of p squared x squared, you have to actually add in this half h bar omega to make sure that this expression on the second line is exactly the same as the expression on the first line. And defining these operators A in A dagger, sorry. Which is basically just the factor of square root of omega over h bar out from this expression for this complex variable x plus ip. And this is the definition of A and A dagger. Then from the expression for the x and p commutation relation, you can immediately write the commutation relation between A and A dagger. And using this A and A dagger, then Hamiltonian is now written in this familiar form. H bar omega is factored out. And what's in the parentheses is A dagger A plus 1/2. And A dagger satisfy this commutation relation. The A dagger minus A dagger A is 1. And I believe that's something you have seen in 137. So here we are starting with this Hamiltonian for the harmonic oscillator. And we are doing only rewriting of it using A dagger. So classically, that's exactly the same thing of writing the absolute square of the complex number in terms of the real part squared, the imaginary part squared. The only thing that is a little different from classical case is x and p no longer commute. And you have to be paying attention to the ordering between x and p that gives you this 0-point energy of half h bar omega. And then you define this A and A dagger operators. And then it turns out the Hamiltonian has now this simple form, h bar omega times A dagger A plus 1/2. And A dagger satisfy this commutation relation, A dagger minus A dagger A is 1. So any questions about this little review of the harmonic oscillator? Okay, looks like everybody is familiar with this. And then we give this name. So A dagger is called creation operator, and A is called annihilation operator. Of course, in the case of harmonic oscillator, you're not creating anything, you're not annihilating anything, they are just names. But as you know, acting A dagger on a state raises the energy to go from one state to another state with a higher energy. So you might say you're creating energy in the case of a harmonic oscillator. And also when you act A on a state, you go from state to one state below in energy. So you might say you are annihilating energy. But at this point, you're not creating a particle or you're not annihilating a particle. The only thing you're doing is go up and down on the spectrum of the energies for the same system. So that's the idea of the creation annihilation operator. So some textbooks uses this name of creation annihilation operator. Some other textbooks uses the name of raising and lowering operator. And I would say for a harmonic oscillator in particle mechanics, raising and lowering is probably a better name. But I use this name creation annihilation operator because we end up using these operators literally for the purpose of creating a particle and annihilating a particle later on when we go to field theory. So hence I'm using this name over here. So at this point, I'm only talking about harmonic oscillator in mechanics, particle mechanics, not field theory. So the names are just names, but I'm calling A as an annihilation operator, A dagger as a creation operator for later purposes. Okay, now that we have this Hamiltonian operator, I can define the ground state. And the first thing you learn is that ground state, the Hamiltonian operator is bounded from below. So whenever you take an expectation value of this Hamiltonian operator, then you have this 0-point energy half h bar omega. But the first term A dagger A is also sandwiched between the state psi, no matter what the state is. But the point here is A dagger is a Hermitian conjugate of A operator. So A is now acting on psi, and I let A dagger act on the bra psi, and A dagger acting on bra psi is just a Hermitian conjugate of A acting on psi overall, because psi bra is a Hermitian conjugate of psi ket. So the first term is now written as an absolute square of A acting on psi ket. And the absolute square, of course, is positive semi-definite. It cannot be negative. So as a result, the first term is actually semi-positive definite. So it's bounded from below by 0. second term is just a number. So as a result, this expectation value of the Hamiltonian operator is always larger than or equal to half h bar omega. And because Hamiltonian is now limited from below, the smallest it can be is half h bar omega. And for Hamiltonian to have the smallest possible value, then the first term, A acting of psi, should vanish. So that immediately tells you that minimum energy or ground state is obtained when the A operator gives you 0. So if A operator completely makes the state vanish, in other words, if annihilation operator A annihilates the state 0, and that is now the ground state of the harmonic oscillator. In recording, the annihilation operator is written in terms of x and p this way. That immediately tells you that the wave function of the ground state follows this very simple first order differential equation, which is much easier to solve than second order differential equation, which is generically what the Schrodinger equation is about. But now that we have this requirement that A has to annihilate the ground state, I can write this differential equation as the first order differential equation because A is first order and P, and that's a lot easier to solve. And in particular, you can immediately see that this equation is given in this particular form of x derivative given in terms of x itself, and hence that actually gives you the Gaussian. So the last line here is that this ground state wave function psi naught is given in terms of the Gaussian in order to satisfy the equation, the second below, from the below. So namely, x derivative is given by x itself. And you can easily check with your eyes that x derivative of the Gaussian pulls out x out of the exponent, and hence that satisfies this differential equation. So this is the beauty of the harmonic oscillator. You don't need to futz around with the second order differential equation. You can easily derive the ground state wave function only using the first order differential equation. Then you can easily see that it is given simply by a Gaussian. And we also define the number operator n, which is A dagger A. And this number operator is useful because it counts how many times you go up in the ladder of the energy spectrum. And that actually in the end turns out to be really the number of particles when you really use annihilation creation operator to literally annihilate and create particles in quantum field theory. But at this point, number operator is again, in some sense, the wrong name. It just is completely redundant with the energy of the system. So Hamiltonian is h bar omega times n plus 1/2. So you can go back and forth between the energy and number operator. So they mean basically the same thing. But when you go to field theory, number operator really does mean to be the number of particles. So I'm using this name of number operator already here, anticipating that. But anyway, so the whole point of this slide is that you can define the ground state very easily using this algebraic method by Dirac, and then you can obtain this explicit form of the wave function as a Gaussian in position x. And over normalization factor script n, and not to be confused with number operator n, the script n is just a number, is fixed by the requirement that the psi naught is properly normalized. Namely, if you take the absolute square of psi naught and integrate over the entire x from negative infinity to positive infinity, it is supposed to give you 1. That's the normalization condition for any wave function. And that fixes this prefactor script n. Here, I'm not writing this explicitly, but that's something you can work out very easily from the Gaussian integral. So again, we have, I believe you have seen this before, but if there are any questions, please ask now. Okay, I'm not, oh, go ahead.
I've actually, when I study quantum mechanics, I already know like the bound, I shouldn't say boundary, but the least possible reached energy should be 0. So, which is why the minimum energy, if you apply the annihilation operator to the ground state should always result in 0. But is this just an artificial trick for us to do, or is there any support of which this is totally like a natural step for us to do?
This is actually specific to harmonic oscillator. If you go to other systems like a hydrogen atom, you don't have the analogous expression for the annihilation operator. So this is actually a magic that works only for harmonic oscillator. And the definition of harmonic oscillator is something where the Hamiltonian is the sum of the square for both x and p. And when you also change the parameters like m and omega, definition of the annihilation operator also changes. But the fact that the Hamiltonian is given by the square of x and p guarantees that something plays the role of this annihilation operator, and you can define the ground state with it. So that's really specific to harmonic oscillator, where the Hamiltonian is given by x squared plus p squared up to the parameters like m and omega.
I see. Thank you.
Okay. Anybody else? Okay, very good. And once you define the ground state, you can talk about excited states. And then this is the place where number operator n plays a very useful role. So Hamiltonian is now written in terms of a number operator. So once you have an eigenstate of the number operator, that gives you the eigenstate of Hamiltonian at the same time. And so that's why they are redundant. They mean the same thing, but the number operator is actually more easy to deal with. The reason being that number operator is now written using the annihilation and creation operator, doesn't depend on any other parameters like h bar, omega, or m. And we have this canonical, commutation relation between the number operator n and annihilation operator a, which you can easily work out. So n is a dagger a. Commutation relation with a, the only thing that doesn't commute with a is a dagger. So I factor a out of this commutator, and a dagger commutator is given by this commutator, the a dagger being 1. So a dagger a commutator is just the negative of that, that's -1. So hence a commutator is -a. And you can do the same thing also for a dagger, and a dagger commutator is plus a dagger. So what that means is that once you have an eigenstate of number operator n with the eigenvalue little n, you can act a on it. And by just going through this algebra between a and n, you can derive that the eigenvalue of number operator acting on a n state is little n minus 1. So if little n ket is an eigenstate of number operator with the eigenvalue little n, a now lowers the eigenvalue for the number operator from little n to little n minus 1. In the same way, then you can also do the same thing for a dagger acting on n. And by going through the same kind of algebra, you can show that the number of the state a dagger n is n plus 1. And in addition, that the a and a dagger changes the eigenvalue of the number operator, you can also define the normalization of each state using, again, simply using this commutation relations. So the annihilation operator acting on state n has a norm given by n a dagger, that's the Hermitian conjugate of an, times an, because a dagger a is number operator capital N, which has an eigenvalue little n. In the end, this actually turns out to be little n. So to properly normalize the state with n minus 1 eigenvalue, then I need to multiply that with the square root of n for the proper normalization. And you can do the same thing when you also raise the eigenvalue n to n plus 1. So hence the normalization factors square root n and square root n plus 1 when you lower or raise the eigenvalue of the number operator. And once you know this, then you have now the entire Hilbert space. You start with the ground state, which is annihilated by the operator A, and then you just keep acting a dagger on top of it to create all the excited states. And you also know the normalization of each state as well, each time giving you a factor of square root of n+1. And hence you have this familiar Hilbert space starting from the ground state 0. You keep acting this lower raising operator A dagger. And each time you raise, you get this normalization factor of square root n+1. So if you start all the way from the ground state, then each time you act A dagger, you spit out this normalization factor of square root n+1. So you can then define the norm of the state after acting the raising operator n times, because you multiply all these factors together, that just gives you the factorial and square root of that. So that defines the properly normalized excited state n as a 1 over square root n factorial after raising the ground state n times using this raising operator. And you can also verify that the lowering a state gives you the proper normalization as well. So now you know everything about the Hilbert space. So the ground state wave function was derived very simply using first order differential equation. It's just a simple Gaussian. And by acting A dagger n many times, and together with this proper normalization factor, you find all the eigenstates of the Hamiltonian. So that's how you describe the harmonic oscillator. Okay, so let me stop here. And then we actually talk about a actually classical limit of a harmonic oscillator using what is called the coherent state on next week on Wednesday, because as we always say, we always think about the particle wave duality. And using this harmonic oscillator with this energy eigenstates is one description. But this description is actually not very good if you're talking about actually oscillating pendulum, because oscillating pendulum is clearly not a stationary state because something is moving. So using this quantum harmonic oscillator, we should be able to describe the classical pendulum because the quantum mechanics contains classical mechanics in it. And the answer to that question turns out to be what I'm calling the coherent state, which you may not have seen in quantum mechanics class. But as you know already, quantum mechanics contains classical mechanics in it. So once you know everything about the Hilbert space of the quantum harmonic oscillator, you should be able to describe the classical motion of the pendulum. And that's exactly what we're going to do. And that's the first step where we start to talk about particle wave duality, which turns out to be very important when you go to the field theory. So I'm using harmonic oscillator as an exercise of trying to understand this particle wave duality. And then we are going to apply that when we get to the field theory. Okay, so let me stop here. If there are any questions, ask now. And I also set up the poll for the office hour. I actually forgot to do this on Wednesday. I apologize. So let me do that today. And I also will post the first homework problem later today, and that will be due by the end of next Friday, as we agreed on after taking a poll on Wednesday. And then we go from there. All right, any questions?
I have a question I might have missed because my Zoom crashed.
Okay.
Can you go back to one slide?
This one?
Yes. Yeah. I'm not sure. For the right-hand side, when we apply the number operator on the state where a acts on number and I would say n. How does the right-hand side, the first line, come out?
Yeah. So because everything is associative, I can get rid of this parentheses on A acting on N. And then
I understand it now. Like I expand the commutator relation and I can
that's it. That's right. That's it.
Okay,
right. Anybody else? Okay. So then that's the end of the class today. And I still don't know why my Zoom keeps crashing, but fortunately, Ryan again volunteered to take the recording. So I will post the YouTube video later today, and then also repost the slides with some updates I have done in the course of it. Okay, so have a good weekend. I'll see you on Wednesday.